Wow, that is an amazing experiment, isn't it? Good morning, everyone. Today we'll be doing an overview on kinetic model of matter. So I will briefly run through the skeleton of this video. So firstly, I will address to you the kinetic model of matter, and then it will be actually shown to you through the three different states of matter, which actually have their principles based off kinetic model of matter. And then we'll talk about the transition between states and within states. For the transition, we'll be also looking at temperature as one perspective, as well as energy from another perspective. Okay, so hopefully this will summarize the majority of learning objectives for kinetic model of matter. Okay, so back to the video. Which one do you think is the cup of hot water? Okay, so as you realize, the answer is right. You are right. Why? It's actually due to diffusion, right? The molecules move from a region of higher concentration to a region of lower concentration. And why is that so? So the key for diffusion is actually kinetic model of matter. There are two aspects. Firstly, we talk about all matter is made up of a large number of tiny atoms or molecules. And secondly, all of them are moving continuously and randomly. So if you remember the Brownian motion experiment, you're able to see the small particles, but they are moving because they are collided by the surrounding air molecules, which push them and collide them continuously and randomly. Now, we know that everything and anything in the world functions based on the kinetic model of matter. Now we're looking at applications of that. So let's talk about water. There are three examples of different states of water, and I'm going to show you how kinetic model of matter is in place. Okay, so I actually went to Harbin recently, and as you can see, I'm doing some ice skating here. So this is actually the solid state. It's very, very slippery. And one day, one nice morning, I was enjoying my breakfast and having my daebing. So this is actually the liquid state. I tried very, very hard to find gaseous state of water, which is water vapor. But I realized that's not quite possible. The closest one you can see is the condensation product. So you realize the humidifier, right, is actually not water vapor, but it is the just condensed version of water vapor. So we can assume it to be the gaseous state. Then I'm going to ask you to infer just by looking and feeling the different states. What is the characteristics of each state of matter? Okay, so it's a good chance for you to pause the video and ponder slightly. Welcome back. Now, solid, let's talk about the volume. Let's imagine a solid. Is the volume fixed or not? It's actually fixed. Is the shape fixed or not? Yes, very, very hard to change. Density is very, very high, right? And not really compressible, or we call it incompressible. Can it flow or not? Hardly, right? Cannot flow. Let's imagine liquid. Now, a liquid has fixed volume. Shape-wise, while water can flow, so I would say not fixed. Density, not as high as solid, that's correct, but also higher than gas, so relatively high. Compressible or not? Can you compress water? Incompressible. Can it flow or not? Yes, right. A river flows. Now, gas. Volume is not fixed. it will essentially occupy the volume of the container, however big it is. The shape, because volume not fixed, then shape also very hard to be fixed. Density, very, very low. And then compressible, yes, you can compress an air, right? It's highly compressible. And for the flow, it can flow. So these are somewhat of an observation. We have got them, and now we're going to look at some application of these. So we're going to zoom in to the molecular level. So now you should be thinking about the molecule demonstration, right? In lower set, you have learned how the arrangement is like. So let's do arrangement first. So you have done the learning for this. Pause the video and let's think if we can remember the keywords. Arrangement. Particles are arranged very close together in a regular pattern. Okay? If we go by row, we realize that the description are very similar, just the change in the keyword. Okay? Now, note the change. For liquid, particles are arranged close together than solid. So there is an element of comparison here, but not in fixed positions. Now, moving on to gas. What is the arrangement for gas? Particles are far apart and not in fixed position. So there are essentially just two key aspects, right? Whether it's close or far apart. That's the first thing. Second thing, whether it's regular or fixed, right? In fixed or not fixed. That's all about the arrangement. Moving on to force. So why is it in such an arrangement? Is it because of a certain force pulling the atoms or molecules close together? So, say with me, in solid, the particles have very strong forces that bind them together. For liquid, the intensity changed. Okay? Strong forces bind particles together. For gas, let's try very weak forces between particles. Last but not least, let us recall on the motion of particles. Firstly, what is a motion of particles? For solid, particles vibrate in fixed positions. Okay, imagine particles really vibrating in fixed positions. Liquid, particles can slide over one another within the liquid. And for gas, particles move randomly and freely in all directions at high speed. So these tables are crucial and extremely important for your preparation for your common test. Now we know that there are three states. We're going to put a variable. So let's say the temperature increases from low to high. And what happens to the particles? What happens to the change in states? And this is when we bring in the idea of heating curve. take water, for instance. Right. At the very start, it will actually exist as ice, let's say at negative 20 degree Celsius. Okay, so as we heat it up, let's say in under a Bunsen burner, all right, so at this stage, it will still remain ice, but the temperature will slowly increase until at zero. At zero, this stage was going on, right? So from pure solid, at this stage, it will majority of the time exist as a solid liquid mixture. And this process is called melting. Until a point where all of the solid have melted. And from this point onward, it will actually become liquid. And then the temperature increase again, and again until, right, in standard condition, 100 degrees, then it will become gas. Liquid mixture. And then it will become water vapor in gaseous state. So take a few moments to appreciate the heating curve. Now, I'm going to ask you to reverse it. So if this process is called boiling, what is the reverse process when gas change back to liquid? It's actually condensation. And what happens when liquid change back to solid? It's called freezing. What about when the solid is changed to gas directly? We call it sublimation. Right. But if you need help in terms of evaporation, which is not covered in this video, drop it in the comment section and I will take note of that. Now, we know that when temperature changes, it will cause the arrangement, the motion, and the force, right, to vary. Now we're going to zoom in this whole situation using another angle, which is the angle of energy. So we learned that energy cannot be created or destroyed, it can only be converted from one form to another. So when we are heating, what form of energy are we introducing to the system? It's actually heat or thermal energy. And when we introduce thermal energy, this system is going to take it and convert it to internal energy. And now, you may have not learned this in lower sec, but internal energy is actually divided into the kinetic energy as well as the potential energy. Let's zoom in. From negative 20 degree to 0 degree, when the temperature increases, it will actually causes the particles to move more energetically and vigorously, vibrate more vigorously in the fixed positions. So in this case, the Ke will actually increase. And now, when the particles have hit 0 degree, it will reach a solid liquid mixture and undergo melting. So here, what is changing? Right, the attractive force binding the particles together is changing. So in this case, potential energy is changing. And Ke remains constant. No change. P in this case, no change or very little change. Now, moving on to liquid, Ke continue to increase because the particles are more energetic as they move around. And then the potential energy, no significant change. Gas-liquid mixture, again, right, there is a huge difference in terms of the arrangement, the force, and therefore the potential energy actually increases. And Ke, negligible change. And further on, the Ke will further increase. So, as you realize that the Ke is actually directly linked to temperature. Temperature increase, average Ke increases. Alright, so that's the bulk of the video. I hope that it can really give you an overview on the topic. Thank you very much.